working? It is working. Yay. Okay. So there we go. We're going to do a little more practice balancing with the PhET sim, the second game. It just has 5 or 6, I can't remember. And then talk about endothermic and exothermic and then reactions and show you a very endothermic reaction, probably the most endothermic one you'll ever see. And then we'll do 2 quick reactions. We will not be doing any questions today. There will not be time. So that's what my plan is, and I'm sticking to it. You guys happy today? Happy it's Friday? Everything's good? It's not that hot. It's not as hot as yesterday. Yesterday was so hot. It is. More than yesterday, but I have pants on. It's good to have pants on in public. Sorry. All right. So let us do a little level 2. So I'm going to call on you, and I may ask you something like, what kind of reaction, or name this compound. So we've got some SO2, some H2, some S, and some H2O. Oh, can you guys see it? Yours is going to come up different, so just kind of watch up here. Okay. Aiden, what kind of reaction is this? A compound and an element, different compound. What are the options again? Pull out your labs, guys. There's 6 types of reactions, right? Is it on your lab? I can't remember now. It's not on there. You have the graphic organizer from before. Give Aiden another second. I'll pick on him later, I guess. I'll come back. Lauren, what kind of reaction? It is not double replacement. Mr. Burt Whistle. Single replacement. Okay. So element makes it single, right? Different element. Compound, element, different compound. One thing is changing places. And what's that one thing changing place? It's the hydrogen and the sulfur changing places. Single replacement. We did it over a couple of days, the graphic organizer. So on the left, I've got 1 sulfur and 2 oxygens and 2 hydrogens. On the right, I've got 1 sulfur, 2 hydrogens, 1 oxygen. So what would be a logical first step? Sorry, I keep telling people that are at home, I should really let them chime in, but I'm a meanie face. Gabby, what would you do first? One, two, two, 1, 2, 1. Add another sulfur?
Yes, wait, so you would have to put another
so the sulfurs are balanced.
the oxygen.
Yeah, we got a problem with oxygen.
The oxygen. So
Okay. Julian? Absolutely. Good. So we got to get the oxygen to an even number because it's even on this side. We have to do 2 times 1. Okay. So once we've got that, that messes up our hydrogens, but that's easy to fix. 2 times 2 is 4. 1 times 2, let's make that 2 times 2, like you said, and we should be good. Yes.
when is oxygen diatomic? When is it? I thought it's always
when it's an element by itself.
Okay.
It's just like, again, I go back to this silly, you go to the egg store, you got to buy them 12 at a time, but you can use 1 or 2 or 3. Same with oxygen. You can use 1 in water. You can use 2 in carbon dioxide. You can use 3 in a nitrate. You can use 4 in a sulfate. There's different numbers that you need depending on what you're dealing with. Okay. Good question. All right. So this one's kind of weird. We've got a hydrocarbon combining with chlorine to make whatever the heck that is, and hydrochloric acid. So on the left, I've got 2 carbons. On the right, I've got 2 carbons. On the left, there are 6 hydrogens. Here's where it gets tricky. There, you see the subscript 5, super easy, right? You got to remember that there's 1 here. So 5 plus 1 makes 6. On the left, there's 2 chlorines. On the right, and this is the other issue, when they're in both of the products, there's also 2 chlorines. So Michael, do we need to do anything on this one? No, I don't think so. Yep. Okay. Next one. Ooh, this is an important concept. So I'm just clicking 1 so you see the molecules. Logan, what kind of reaction involves a hydrocarbon with oxygen making carbon dioxide and water?
I'm not sure.
Okay. Hydrocarbons, fossil fuels.
Combustion?
Yep. Combustion reaction. So let's go through this one real quick. 2 carbons, 1 carbon, 4 hydrogens, 2 hydrogens, 2 oxygens, 3 oxygens. Bethany, what would be your first thing? Always with combustion, what do we start with? Which element? Oxygen's last, so it only leaves carbon. Carbon, hydrogen, oxygen. That's also kind of, that order is for carbohydrates too. So anyway, it's just kind of weird thing. So carbon, fix your carbon. Good. So now we have 2 carbons on both sides. That's good. Next one is hydrogen. How are we going to fix the hydrogen, Colin?
You can multiply H2O by 2.
Yep. And that's a good thing because now we've got even oxygen. So that actually helped us. So this is 2 times 2. That's 4. 2 times 1 is 2. 4 and 2 is 6. Our oxygen needs to have a what? Good job. We should be golden. Yet another combustion reaction of methane. So again, starting with carbon. Do we need to do anything with this, Julian? Nope, carbon's good. Hydrogen, what do we need to do here? Jack B. Just 1? There's 4 and 2, so that's... Oh, this isn't combustion. I lied. Oh my gosh. Methane and water makes hydrogen gas and carbon monoxide. Sorry. So we got our carbons are good. Hydrogens, what do we do? Four and 2, and on this side they go by 2s. So 6 divided by 2 is? Yeah. Okay. And then Amani, do we need to do anything else? I think we're good, right? 1 oxygen, 1 oxygen. Good job. I think we're good. All right. This is not the one either. This methane again, but with sulfur. What the heck? Weirdness. Okay. Carbon and carbon. Gwen, what would you like to do with this? We could. So, or is it 1 plus 3 or?
Sorry, add 2 more.
Okay, so that is a logical way to do it, but let's just look at one thing really quickly that I saw. So I honestly start on the left and work my way through the thing, right? So carbon, hydrogen's got 4. I got them 2 over here. So I would go that way because we're also, that's going to change how many sulfurs we have. So now we do need to add 3 to 1 to get to 4, right? Is that correct now? Okay. Beautiful. Yay. Woo woo. There wasn't 10 of them. There are 2 each, I guess. But anyhow. All right. So some more practice. Never hurt anybody much. Let's talk about any questions from home. All right. On your document, if you have one, a hard copy, somewhere on here, on the front page, it talks about endo and exothermic. You can squeeze in little graphs on here if you want. Actually, the back of all the pages are blank, so you got plenty of room to take notes, but I would like you to take a couple notes on this. So We, I think, talked about this previously. Make two little graphs. On the y-axis is energy. And then just over time going forward. There's two broad categories of reactions depending on whether energy is going in or energy is coming out. Remember that all chemicals have energy, chemical energy stored in their bonds. When you eat food, you're eating food to get the chemical energy from those bonds. Sometimes the reactants have a lower energy than the products. And sometimes the reactants have a higher energy than the products. The energy is stored in the chemical bonds. In this particular case, since the products, the stuff you end up with, has more energy in it, the energy has to come in from somewhere. Okay. On the other hand, most of the reactions you'll ever see, the reactants have more energy in them, like putting a piece of wood on the fire. There's more energy stored in that wood than in the ash that remains or the gases that go off at the end. So the products have less energy. The energy is going out. Okay. This is called the change in enthalpy, and for some unknown reason other than the fact that H is for heat, that delta H, the enthalpy for this one is positive because it's adding energy to the system. The delta H for this one is negative. It's losing energy. That's called enthalpy. It's a weird word. Okay. All right. Turn to your neighbor, tell them which one's endothermic, which one's exothermic. This is always kind of tricky. Gale, what do you think? What's this one? This one's endo. The energy's going in. Exothermic, it's going out. It's exiting. Less energy in the products. That's because it's products plus energy. This goes out. It exits. Okay, it's exothermic. This one is going in. It has to come in from somewhere. It comes in from your body when you're touching it. It comes in from the air. It comes in from the counter. The products are higher, okay, which means it's the reactants plus energy. So energy would actually be on the left-hand side of the equation. And there's very specific numbers that go with every single chemical reaction. So it's going in, and that's endo. So again, how would you perceive it? You would perceive this one as hot or warmer, okay? This one, it's going in, it's leaving you. You would say this feels cold. Now, I'm going to show you an extreme example of that in just a second. But there's one other thing I want to talk about, and that's this value of energy. How much, what is this peak of this little hill called? It's just like in the Hindenburg, you know what? That was a ginormous explosion of hydrogen. It didn't start by itself. It needed a little push, okay? It needed a little bit extra to get it going because you have to break up the reactants before you can reform the products. To get activated, you have to give it a push. So this is called the activation energy. Okay, it's a little extra you have to put in. All reactions, no matter how extremely exothermic they are, still need a spark, right? Your burner doesn't light by itself. Okay? You had to use a match or a striker. Every reaction requires a little bit input. Every reaction gives out some too. It's actually the difference between the two of them that causes it to be endo and exo, but that's a story for another day. All right, what do catalysts do? They knock that activation energy down. Adding a catalyst causes the formation of intermediary species that allow the reaction to proceed with less input energy. Okay, so we take that bump down like we did with the hydrogen peroxide and the manganese dioxide. We lowered the required input to get the reaction going. While you're finishing copying that, I'm going to mask this out. So I'm going to mix together two chemicals. And I'll tell you what they are in just a second. Fortunately, they're very hygroscopic. They absorb water from the air and they chunk up, which is kind of a pain. Come on.
So is brown sugar hydroscopic?
Hydros. Yes. That word. That's exactly. I used that example in Australia. That's good. All right. So this first chemical is ammonium thiocyanate. So you know ammonium is a +1, thiocyanate is a -1. And making a mess of the place. The other compound is barium hydroxide. See if you can come up with that formula, anybody. Shout it out when you can. Barium hydroxide.
BrHO2.
BR?
Oh, sorry. I think bromine.
Anybody?
BaHO2.
No. That's right. So you don't finish on it? Oh, that's a little bit more on that too. So BA is correct. Let's charge on barium. Group 2 +2. And then hydroxide. Hydroxide, OH, and it's a -1, and you need 2 of them. Okay. All right. So, I need my stuff. You said HO2 or something like that. All right. So I have 2 flasks, and they have 2 white crystalline solids. Technically, they're salts. And I'm going to put them into this flask that is mostly dry. Yeah, actually it's pretty dry. I had to rinse it out from earlier this morning. Last period I did this over my computer. That's a bad idea. What are you going to do with me? Okay. And again, they're both dry and there's no liquid yet. Okay, so these 2 chemicals eventually would probably react on their own, but it takes a while. So I'm going to activate them by shaking them, right? All we're doing when we heat things up and stir things up is we're making the molecules move faster. That makes them have more collisions. That makes it more likely for them to react. So very quickly, it starts to kind of clump up more. It's not dry anymore. It's wet. And pretty quickly, it's going to get slushy. So I'm going to put some water on this piece of wood. I'm not putting the water in here. And now it's really slushy, right? It's liquid. Okay, I'm going to put that on this, put this on the wood. And I used to do this. I used to have a piece of 2x4, but this is good. I'm going to let it sit there for a second. And pretty quick, you can see it's condensing and it actually freezes to the bottom. So go ahead and touch the glass. Cool. So So if you've ever used a cold pack where you have to break it open, like you hurt your ankle or your elbow or whatever, you hurt yourself in a sporty fashion, it gets really cold. Yeah. And it's just sucking in all the energy out of the room into the chemicals. And it froze the wood to glass. So now you guys know what I'm talking about with the cold packs where you like have to smack them and shake them up? That's what this stuff is.
Yeah, like,
It's the exact same stuff. And so the crazy thing is I didn't add water. One of the crazy things, besides how cold it gets, is that there's actually, so that was this reaction, extremely endothermic. Barium hydroxide is what we call a hydrate. So we put these little sticky dots, like little adhesive dots for scrapbooking and stuff. So barium hydroxide, each unit of barium hydroxide has 8 water molecules incorporated into its crystalline structure. You can't see it. It's locked in place in the crystal. But once you get it agitated, okay, those can break off, and then that starts the reaction between the two chemicals. It's very endothermic. And when we have two chemicals like that are going together, what kind of reaction is innies and outies? Double replacement. And so we're going to end up making barium thiocyanate and ammonium hydroxide. And yeah, it's pretty crazy and still frozen. And it stays really, what the heck? What temperature is? That's awesome. I should have done that before. It's at minus 16.6 right now, minus 17. Wow. Chemistry is so cool. I try. It's Friday. 18.2, minus 18.2. What the heck? Okay, crazy. Minus 18.2. All right, let's look at our lab and see what you're going to do today. You should have gotten through. We got through magnesium and oxygen. Awesome. We're on zinc and hydrochloric acid. We get to blow something up. Yay. Appropriate. So we're going to use the 6 molar hydrochloric acid. The zinc, remember, is in these blue cap tubes. Yours may be kind of powdery. It may be little chunks. It says add 3 small pieces. It depends on what size pieces. So add a small amount. Mine's like flakes. So add a small amount to the test tube. And then the 6 molar hydrochloric acid. It says 5 drops. Go wild and crazy and put in 10. Okay. What up? So danger, danger, Will Rogers. Okay, so you get 10 drops of hydrogen chloride in the test tube with the zinc. Then you need to cover it with your watch glass. Leave it in the rack. Let it sit there and react. Find a splint and light it. Make sure it's burning well. And in 30 seconds or so, then coordinate with your partner. One of you take the watch glass off and the other one put the splint immediately, can't emphasize that, like really fast into the mouth of the test tube. And if you really want to, you can do it multiple times, but you have to let it react. The grody looking beaker up here in front of Jack is for your zinc. If there's any zinc in the test tube, rinse it out and then you're done with that. You need the watch glass for the next one. So let's just do this. So you're taking solid zinc and you are reacting it with 6 molar hydrochloric acid, which is aqueous. And I'll let you figure out what's happening. One of the things that's happening is hydrogen gas is forming. And that gas, oh heck, there we go. That gas needs to be tested with a lit splint. Okay. Okay. And then
You said 10 drops.
I did. I said, go cray. Okay. The next one is sodium hydroxide. And this is also aqueous. It's in one of the little bottles. Make sure you pay attention to what you're trying to do, because people were putting the wrong things together because they weren't reading labels earlier. And you're going to use the 1 molar hydrochloric acid this time. And in this one, again, make sure it's sodium hydroxide to start with. You got to read the labels. This time you're going to put those onto the watch glass, 10 drops. Make sure you count. And then you're going to add phenolphthalein. Phenolphthalein looks like water. It's in a bottle, looks just like water, but it is an indicator. And so you're going to record what happens when you put that indicator into those drops. And then it says use a toothpick. We don't have any toothpicks, but it's super easy. You're going to break off a piece of the splint. If you need new splints, let me know. They're getting kind of end of the week here, but maybe a little bit bigger than that, maybe like this. This is going to be your stir. So you got base and phenolphthalein. You're going to add drop by drop 1 molar hydrochloric acid onto that solution and stir it up and say what happened. And then that can just get rinsed into the sink. Okay. Questions? All right. Goggles, hair ties, aprons, shoe covers. Go have fun. Those of you at home, I will post the videos before we end the day, or I